Let's jump straight in. Following on from the video on waves basics, you might have seen it already. Okay, let's jump straight in. What have we got? What happens when waves meet? Okay, so here is one wave, here is another wave, exactly the same, traveling in the opposite direction. What happens when they meet? They double up, don't they? So we call this superposition. When waves meet and they add together, that's superposition. And we call that, when they add together and they become bigger, then we call it constructive interference, and they've added together and then they go back to their normal selves, back to their original size, and carry on in their respective directions. Here we've got another one, same, just the only difference is this is a positive wave and this is a negative wave, traveling in opposite directions. What happens when they meet? They cancel each other out. Okay, so we call that it's also interference, but we call it destructive interference when they lessen, when the waves cancel each other. That's called destructive interference when they reduce in size. Okay, let's have a look at the next screen, what we got. Okay, so the principle of superposition, let's just quickly read what that says. Principle states that when two waves meet at a point, the resultant wave is the sum of the displacements of those two waves. Okay, so we can pause that. We can remember what is the principle of superposition. Okay, next. Yeah, and what we just talked about, constructive interference and destructive interference. Okay. Here we can see more about this constructive interference and destructive interference. I want you to look at these two waves when they're added together. What's that going to be? Is that constructive interference or destructive? And what about these we've got here? Is that constructive or destructive? Just pause the video, have a think. Okay, answer is, of course, these two add together, they're in phase, and when every point on the wave is going to double up, basically. Okay, so let's have a look. In phase and constructive interference, and this one is 180 degrees out of phase. Don't worry about too much about this in phase, out of phase. We'll talk about that later. That's just saying they're opposite, basically. If they're 180 degrees, then they're doing the opposite at any given point in time. And this one is cancelled each other out, so it's destructive interference. Okay, now let's have a look what we mean by these two terms, in phase and out of phase, whether they're in phase or out of phase. Well, we can represent a wave, a moving wave, on a circle. So one complete wavelength would be one complete circle. And we can see how that is represented here, because if we just turn the circle, you can see at this point, it's just going up and down. So here we can see it as we move around the circle, how the graph is plotted there. And obviously we prefer to use radians in physics or in maths instead of degrees, because it makes calculations more simple. So don't forget there's 2 pi radians in a circle, so 180 degrees is going to be pi radians. And then we can know that, you know, if 180 degrees is pi radian, so half of that is going to be a half pi radian, that would be 90 degrees. And 3/2 pi radians, that's going to be 270 degrees. Okay, so now we can see superposition in action here. So instead of just one wave going across, we've got 2 waves doing exactly the same thing, so we can say they're completely in phase. So when this particle is at the top, the other wave's particle is also at the top. The waves are doing exactly the same thing, isn't it? And what is the result of that? Well, we get double. When the waves are combined, we get double the amplitude and the same frequency, but just double the amplitude there, so double the displacement of the wave. Let's have a look if we change these values. So what will happen at 90 degrees? Gone a bit too far there. 90 degrees, don't forget, is pi over 2 radians, or half pi radians. Okay, so now we can see that the green wave is leading the red wave. You can see it's in front, and there is 90 degrees separating those waves. Now if we go up to 180, what happens now? This is what we call completely out of phase. This is when two waves, when you add them together, they cancel each other out at every single point on the wave. So the result is no wave. Okay, let's take a look at this question. The diagram shows a wave passing through a gap. Which property of waves is being demonstrated? A, diffraction, B, interference, C, superposition, or D, polarization? Pause the video and try and figure it out. Okay, the answer is diffraction. Diffraction is when waves are bent as they pass through a gap. Here we can see the waves are bent. Okay, next one. Pause the video, have a go at this question. Okay, welcome back. The diagram shows two loudspeakers connected to the same signal generator. Signal generator is here. A girl walks from position A to position B. Which statement describes what she will hear and give the correct reason? Okay, because this is, they're using the same signal, so the waves are going to be coherent. That means we're going to get interference. So when she moves from A to B, there's going to be periods where she has a maximum loudness and periods where she has a minimum loudness. So this is superposition, isn't it? Yeah. Waves are going to be in phase. Waves are coming from a coherent source. So there's going to be places where the waves are in phase and out of phase. So answer, let's have a look. A rise and a fall in the loudness as the waves go in and out of phase. That is correct. Have a look at this one, pause the video. Okay, welcome back. The diagram below shows the displacement time graphs for two waves A and B. Okay, so we've got wave A here and wave B is here. What is the phase difference between the two waves? So we want to be looking at different points on the wave. We can see they don't have the same amplitude. Wave A has a bigger amplitude than wave B, but what are they doing at certain points? Well, it's easy if we look here. They're crossing here at the same time. This point. Here it looks like they have maximum displacement. Here they're crossing again. Here they have maximum displacement. So they seem to be in phase, don't they? Yeah. So if they're in phase, sorry, they seem to be exactly out of phase, doing the opposite thing to what what they're doing. So we're going to say that's 180 degrees or pi radian. The two waves A and B are combined. Name the type of interface that will occur. Sorry, interference that will occur. So when they're combined, if they're out of phase by 180 degrees, we call that destructive interference. Let's have a look at some terms that we need to know. Diffraction on that first question, this is the spreading out of a wave when it passes through a gap or around an edge. Diffraction is greatest when the gap is approximately equal to its wavelength. Interference is what we observe when two or more waves meet. So where waves interfere constructively, we observe high intensity. So that is when we've got superposition. Waves are adding together, they're having a higher amplitude is increased. So sound is loudest, light is brightest. And where waves interfere destructively, we observe low intensity, no sound, no light. Just coherent sources we talk about with that speaker question. Coherent source, so a coherent source is emit waves that have a constant phase difference. So if we think about one wave, then all of that entire wave train is going to have a constant phase difference. So that's why when we want to get interference, we need coherent sources. The only way to really do that is use a single source and then split it up, which is what we saw with the speakers. Then we're going to get interference where there's going to be loud bits and quiet bits where it's cancelled out. So let's take a look at how a standing wave is formed. So if we imagine one wave just travelling along a string here, and it gets to the end, which is a fixed point, it's reflected at the other end, and then it comes back along. This is the basic for understanding how a stationary wave is formed. So if we now go down and we look at a series of waves, so a train of waves, they're going along the string, and then they're being deflected here, and what we're getting is superposition between the wave travelling in this direction and the wave travelling in that direction. And the result of this superposition is a stationary wave, where you have areas where there's zero displacement, they're just fixed, and areas of maxima and minima. Okay, so we can see more clearly here an animation of how a stationary wave is formed. So we've got our two waves that are traveling in opposite directions. Let's have a look. This blue one is going along this way, and the orange one is traveling in that direction. We can probably see that what are we going to do if we increase the frequency, what happens there? Yeah, we can see that, look, this wave is traveling nicely along. We can follow it along. This wave is traveling nicely along here. And the result of the superposition of these two waves is the green thick line here, and you can see that there's stationary points. You get these stationary points, and then the maximum minima are just moving up and down. These stationary points are actually called nodes, N-O-D-E-S, and we say these points of maxima are antinodes. So we've got a node, an antinode here, another node here, an antinode here, a node here, and an antinode here, and then this one is not quite a node. But if we try that at different frequencies, you can see what happens. It's quite interesting. You can just see how we get a stationary wave forming from the superposition of the original two waves that have the same frequency, so they're coherent. And when we get a stationary wave formed, the points of zero displacement are called nodes. The points of maximum displacement are called antinodes. The separation between adjacent nodes and antinodes is half a wavelength. So here we've got a transmitter. This is actually an antinode. You can see here that the waves are not coming directly. They're coming out of the transmitter as an antinode. Here we've got a node where there's zero displacement, node, and we can see that one wavelength is all the way to here, isn't it? So half a wavelength is the distance between adjacent nodes. And we can see here that the separation between a node and an antinode is a quarter wavelength. So one node here and an antinode, and of course that is a quarter wavelength distance. We can also say that the phase difference between a node and an antinode is 90 degrees, or pi over 2 radians. Okay, so here we can see that a length of string here, and when you vibrate the string to get these stationary waves, we can call the first stationary wave, which is formed, as this one, where it's just going up and down, up and down. And you can see that this is half a wavelength, isn't it? Yeah. So the distance L, half L, equals one wavelength. So sorry, half a wavelength is equal to L. isn't it? Yeah. So one wavelength equals 2L. That's what we've got there. We call this the first one the fundamental. Okay, then the next stationary wave that you're going to get formed is the second harmonic, where we can see we've got one whole wavelength here, and one wavelength is equal to L. So we've got one wavelength is equal to L there. Then the next, so when you're going at a certain frequency of vibration, then we get the next stationary waveform, which is the third harmonic, and you can see here that 1.5 wavelengths is equal to L, the length of the string. So we can say that 3/2 wavelengths is equal to L times by 2 divided by 3. So we get 2/3 L is equal to 1 wavelength. Okay, now let's look at how, so that's waves on a string there. Let's have a look at another way is stationary waves in containers. This could be open at one end, or it could be open at both ends. To get a stationary wave, it's going to be, different. But here we've got a tube which is closed at one end. The distance of the tube, the height of the tube there is L, or the length of the tube is L. What have we got here? So the fundamental, the first wave formed, is actually 1/4 of a wavelength. We can see here. We call that the fundamental. So in a tube that's open at one end, the first stationary wave that is formed is 1/4 of a wavelength long. So one wavelength would be equal to 4L in that case. The second harmonic formed is actually 3/4 of a wavelength. So one wavelength is 4/3 L. The third stationary wave formed is equal to, now we've got what, 1.5 wavelengths, so 3/2 wavelengths. Oh no, it's not quite 1.5. It's 1.25 wavelength there. So 1.25 we can say is 5/4, and that's equal to 4/5 of L there. And then we can have a look at these pictures. We can see that this is a node at this end. This is a node. This is a node. This is an antinode here. Here we've got a node, and then the antinode here, and an antinode here. Node, 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 antinode, antinode, antinode. Okay, and it's good to remember that the fundamental, the second harmonic, and the third harmonic. Pause the video, have a go at these questions. Okay, here are the answers. Just go ahead and check those yourself. If any questions, please put them in the comments, and I will get back to you. Okay.